The first presentation this morning is from Dynamic Ratings. Chris Rutledge is applications engineer for the company. He joined Dynamic Ratings team in July 2019. Prior to his present position, he served as substation asset manager and chairman of the Substation Safety Committee at Memphis Light, Gas, and Water. Chris has 27 years of experience in the utility industry, primarily focused on the installation, service, and maintenance of both substation and distribution equipment. Okay, Chris, so if you would share your screen, we will start with your presentation.
All right. Hey, good morning, everyone. And thank you for attending. Glad to have you and hope you can take something away from this. Today, we're going to look at hydrogen monitoring solutions, and this is primarily concerning network type transformers found in vaults. As Randy mentioned, I come from Memphis Light, Gas, and Water. Actually, we have the oldest network system in the country. It was established in 1907 was when they first went into service with it there. So we had quite a bit of older equipment that we were using, and we were starting to see a high level of failure. So at that point, I was tasked with trying to find some solution to monitor these, to prevent these failures. So that was kind of what got me started down the path of looking at monitoring of network transformers. So just a quickly preface, just to go over what these are for those of you that don't know. Network transformers typically located in your downtown areas and larger cities to mid-sized cities, and it's really a means of having a improved reliability for that part of town. So you can have multiple circuits coming out of your substation that are feeding 3 or 4 or 5 transformers in a vault. So that particular grid that's on is being supplied by multiple circuits, distribution circuits coming from your station. Therefore, losing a single circuit doesn't really affect the reliability of that network. So these vault or network transformers, as I was talking about, they form these grids, and typically, if you go, you'll see them. If you walk over grates downtown, they're located in underground vaults. Occasionally, they're located in a walk-in vault that'll be in the basement of a building. However, these failures, especially ones related to cable compartments of this transformer, anytime you have a catastrophic failure, there's quite a bit of liability and cost as a result of that. I've seen actually had customers injured as a result of these. We've seen building fires. A lot of damage associated, and then of course negative media that goes with that. So when I got to really looking at these and trying to figure out, okay, how do I prevent that? I went to all the vendors out there on the market, and you were running into the price point of the equipment, because the transformers are not terribly expensive in relation to, say, a substation transformer where you're spending $2 or $3 million. So PD was one option I had looked at. Of course, that was really hard to find in a price range that was going to be effective. And so I ended up going with hydrogen monitoring. However, everybody's hydrogen monitor seemed to only be for main tank, and I just wasn't seeing enough failures occurring in the main tank. That wasn't where the bulk of my problems were coming from, but I definitely, the monitoring of hydrogen gas was going to present the most economical solution for monitoring these. So also it had to be something that was a fairly simplified setup. We at the time did not have complete comms communications network set up to all of our vaults. So we had to kind of look at either, and we did get in the process of getting some fiber run, but we explored some options of some wireless communications. And this was back before the IoT has got to where it's at today. So it was a little more complicated. but these were just some of the things we had to take into consideration. And then there should be a minimal cost of ownership. We don't want to put something down there. One of the main problems we were having was we had so many of these transformer vaults, and I think Memphis is sitting on about 605 network transformers, or at least when I was there, somewhere in that range. And I did not have the manpower to go in and do the inspections as frequently as they needed to be done to these transformers. I mean, we did do an inspection, and being out in the industry and talking about how some other people handle the service of these transformers, we actually had a very good program in place concerning doing the maintenance of these, which is something I'll cover real quick, and I don't want to spend too much time because I need to get in the conversation. But I've talked to a lot of customers since I've been on this side of the industry, and I'm finding that a lot of them are not looking at pressure of the transformers or even worrying if there's nitrogen on the transformer. And so with this, these are subject to be submersible. So you do risk moisture ingress in these transformers, and that's a big piece of the failure. I can't tell you how many times I've been in a vault where a cable compartment had developed a leak and all the oil had run out on the ground. I mean, and you don't have a lot of clearance in there. You need that dielectric. So any moisture ingress is really exasperating that chance of that failure happening. So that was just some of our maintenance procedures where we would go in, we would always make sure that we had positive pressure on these transformers to keep moisture out. We would typically do an oxygen analyzer to make sure that we had no oxygen present in the system. And then also we would take a Tcg test, which I will go over in a further slide. Tcg test, for those of you that aren't familiar, was the precursor to our DGA testing. You take a sample of the gas space. It's run through a tester that has a catalytic bead type sensor in it. So it simply detects levels of combustible gases without really telling you, it's not breaking it down into what gas you have, hydrogen or acetylene. It's just saying that you have a lot of gas there. You probably should examine the unit more closely. So that was kind of our routine maintenance for these. But again, with the lack of manpower and having the service, of course, substation transformers taking priority, and then distribution transformers we were having to look at for customers, the larger pad mounts. It just was really hard to get down there as often as was needed to keep these in good working order. These vault failures can be catastrophic. I've seen, and there towards the end of my career, maybe once every other year, we would have a catastrophic failure of one of these, resulting in some type of fire in the vault. Also, there's quite a bit of explosion associated. If you've ever want to go through YouTube and take a look at these, there's plenty of videos, especially that cable compartment being such a small compartment, holds about 8 gallons of oil. When that explodes, you're trying to contain that arc flash in a very small compartment. So it's really an impressive thing to see when one of them goes up. And then the proximity of these vaults, again, they're under sidewalks. Often in your tourist areas. I know in Memphis here, we have several that are Bill Street, Main Street downtown. So you always have that risk of customers being in close proximity of the vault, as well as property damage associated. So during these vaults, as I was talking about, we have 3 compartments when we're looking at these transformers. The main tank, and that's where our core and coil assembly is. That's the largest compartment of the 3, probably about 300 gallons of oil we're looking at in those. We go to the switching compartment, and this is a switch that is for grounding purposes that's built into the transformer. It's maybe 15 to 20 gallons of oil in it, so a much smaller compartment. And then, of course, the cable termination compartment with the 8 to 10 gallons. So these are are very susceptible, these smaller compartments, to rupture, just because the internal pressure during any type of fault grows so quickly, and there's nowhere for expansion to happen. When they do, again, you almost always have in the cable compartments or switch compartments failures, there's almost always fire as a resulting of that. And then manhole covers, that kind of thing. I've seen vault grates blown completely out in the street, into hit cars, that kind of thing. So a lot of these covers can become projectiles during these events. So while these are more of the not really network transformers, but the best graphic I can show you, this is just some of the media exposure you would see. And like I said, every time we have one of these fail catastrophically, we were on the news that night, which is something no utility really wants to see. You don't need that negative publicity, but we can see in this event, this manhole cover was blown 30 feet away from where it was located. The covers on top of the vault were buckled up, and there were some windows shattered, and some fire associated with some of the stores in front of this, which is something else to look at if you're in your town. I would find quite often you would find businesses that would place smoking areas over these vaults, outdoor patio eating type areas that would be very close or on top of the vault itself. Just another safety thing to take a look at when you're maintaining these networks. Again, the biggest concern with these failures is, of course, you always have the cost of replacement, but it's really a safety issue is what we're really dealing with more so than anything. So transformer protection, generally your protection goes back to the substation. It did for us. So your circuit breaker, distribution circuit breaker, is your protection to the high side of these transformers. I have been in a few utilities where they have put a vacuum interrupter in the vault with the transformer. So I'm starting to see more of that beginning to happen. But before, it was always just like any fault that occurs on any distribution line, it was reliant upon the breaker at the substation was really all the protection you had for the primary side of these transformers. They do have protectors on the low side. However, these aren't really to prevent any kind of fault from the high side of the transformer. These are just there to put that transformer into where it's injecting power into the system, or it is locked out of the system, to prevent reverse power flow coming back from the grid through the transformer. So this is a typical network transformer. You're seeing some different designs coming out now. This is traditional 3-compartment. So if we look here, we see this is our cable compartment. This actually only runs back to about this seam right here, so you get an idea of how small this compartment is. And you'll have your primary coming in here. We ran 13.2 on ours. And then you have a switching compartment, which is this switch, which will allow you to ground A phase, B phase, or all 3 phases of the transformer when the transformer is out of service for maintenance and testing purposes. This compartment actually goes up behind the cable compartment, and there is some bushings that feed through here, and then bushings from the switch into this main tank back here, which is where our coil and core are contained. So that's the 3 compartments we're talking about. I'm seeing some designs now where they may get rid of this and have these in a single compartment for the switch and the cable terminations. A lot of people are coming with EPR elbows into the front of these now. So you're seeing some different types of setups to try to alleviate some of the failures that are associated with these. But that being said, when you're considering monitoring of these transformers, you really have to take a look at each compartment. I've seen a lot of online monitoring, and this was the problem I was having when I was trying to find monitoring myself, was they were putting monitoring in the drain valve of the main tank. So the traditional hydrogen monitoring in oil, through the drain valve. And by doing that, you're actually missing this cable compartment and the switch compartment completely, because these oils are not mixed at all in these transformers. So anything that were to happen in this cable would not be detected by any type of monitoring on the main tank. And the same as goes for the switching compartment as well. Also, there's some other things that need to be considered when we were talking about maintenance, and something I took into consideration when designing monitoring for these faults. They flood a lot, and even in Memphis, we're definitely not a coastal area such as New York, where they really struggle with this. But we would have water mains burst in the winter. We would find these transformers underwater, and as much as 15 feet underwater at times. Sump pumps gets clogged up in the vaults. You do have all your water mains running there. So moisture ingress and integrity of this tank and all the gasketing system is a big factor in ensuring that these transformers stay healthy. When you get, again, a lot of people I'm seeing are say, well, we don't worry about pressurizing, or we're not checking pressure. That's a critical point with these transformers, and really with any nitrogen blanketed transformer. I see a lot of concern about moisture monitoring, which I think is vitally important to transformer monitoring. However, if you have a transformer that is holding nitrogen pressure and you do not have leaks pressure, that really alleviates a lot of the moisture concerns. I mean, the moisture, it's definitely something you need to know about your transformer, the moisture level in oil. But in my experience, when I found that a transformer is wet, that's really a big headache at that point to save it. When you get into a larger substation transformer, of course, you can vacuum process with hot oil bath and vacuum process that transformer until you can get it dried out to some degree. But when you get down to these smaller transformers like this that may not be rated for that level of vacuum, there's really no way to dry them out. So my thought process for this is, I would rather prevent the moisture from the beginning and avoid that moisture ingress, rather than have to worry about it on the tail end of, okay, now what am I going to do about it? Because again, I've untanked, I've tried drying in ovens, I've run the offline dry out systems for 6 months, and all of this does help, but I've never really been able to get one back to a good dry state after that moisture ingress has happened. And then, of course, with coastal regions, we're also looking with that flooding, you have that salt corrosion that's also a huge issue. And then cost effectiveness, as we've already talked about, $80K is probably a little high. I don't remember the exact cost, but that is the cost of the transformer with the protector. The transformer itself, we're probably looking at somewhere in the $30,000 to $40,000 range, maybe a little less depending on the size of the transformer. I've seen these anywhere from 500 kVA up to 3,000 kVA. So that's another thing you have to consider with monitoring. Nobody's going to let you throw a multi-gas monitor on something that costs $80,000 with the multi-gas running you 30 or 40. So it's just not a realistic solution to this problem. And lastly on this, again, really when considering the monitor, and this is something that we do a lot of, we've recently introduced some breaker monitoring into the market, and with these, it's the same thought process I have with these. You really got to consider your reasons for putting a monitor on something, and it's not always directly related to how much did the piece of equipment cost that I'm putting the monitor on. With these, it's a huge safety problem, and it's a logistic nightmare to change them out. I mean, it's cranes shutting down streets to get in vaults. The same with breakers. I see, $2 million transformer. Nobody bats an eye at putting $100,000 worth of monitoring on that transformer, and yet you look to the right and there's a high side breaker protecting that transformer. That is the main means of protection for the transformer, and it was installed in the 50s. And there's nothing looking at it. And the same for the bank breaker, the protector on the other side of the substation transformer. we're not looking at them all. We're doing a 5-year maintenance cycle. And again, I've seen several transformers fail simply because a breaker failed to operate. But that would be a talk for another time on with this one. So these were some pictures I had of some actual failures, and you can see that these do most frequently occur in this cable compartment. That was where I was seeing most of my failures happening. And I would say, when I say most, I'm thinking 85, 90% of the time, this was what I saw after a failure. Now, the interesting thing about this compartment is there's no real means for maintaining this compartment. The cable compartment is typically filled with oil. There's nowhere to really take a gas sample unless you take the plug out, at which case you've lost your gas sample. You can do some oil sampling of it from the drain if you want to run DGAs. But another interesting thing about this compartment is it is the only compartment on the transformer that it's not normally pressurized. So you really don't see, you're not aware that you have a leak with this one, or it's hard to be aware that there's a leak happening. So typically when we look at these, this is where our cables, and it's just simply cables coming from outside the transformer into this compartment, and they're terminated where they go into the switching section of the transformer. This is really not that hard of a failure to detect. Typically, when you start seeing breakdown of these cables, that's usually a pretty good PD event prior to the failure actually happening. And that's easily detected through hydrogen monitoring. Again, PD monitoring would be great if that was, but it's not really a cost-effective solution to this. So that was something else I took into consideration when looking at these when we built our system for monitoring. So existing, kind of what I was seeing out there, people were looking at oil levels, they were looking at oil temperatures, the status of their protector. Most companies are bringing that into their SCADA to know if the protector's open or closed. And then there's a lot of monitoring involved. Some of these vaults can get pretty hot depending on what's going through them. So ambient temperature, float switches are definitely a must-have for detecting flooding level in the vaults. Light, Gas, and Water actually had a great pump controller they had patented when I was there. I had no association with that at all, but we had a motor shop that developed a sump pump controls. They would have up to 1 million operations for their controls. And that's just a little shout out to my guys there at the company. I thought that was very impressive what they came out with. But what you're not seeing a lot is people aren't doing any monitoring of the switching compartment. Any monitoring of these cable compartments. And typically, if they're doing any kind of monitoring that would provide an indication of problems occurring within the main tank of that transformer, it would only be hydrogen monitoring through the main valve of the main tank. So by looking at these temperatures, even bringing in hot spot temperatures, not really a good indicator that you have a problem, an incipient fault starting to occur. You're not going to see a big swing in the operating temperature that would be noticeable because that heat dissipates so quickly into the oil. And this, again, goes for any transformer, be it a substation transformer or a small distribution transformer. Unless you can, the minimal that you can do is get a sample of either gas or oil from inside that transformer to really have any idea if you have a problem starting to occur, because you're not going to see it in the load and changes in load, changes in temperature. Those kind of things really aren't going to tip you off to the early stages of these problems starting to happen. So traditionally, temperature, pressure, insulating fluid level, and some people do dissolved gas on these. They'll go down and pull. They'll pull their DGA samples occasionally. Of course, again, that's not normally a priority, and it'll get done when it gets done on whatever cyclic type maintenance they're doing. And you do have to do all 3 compartments, and that's something I really want to keep emphasizing. If you're only looking at main tank, you're really missing the boat with this one. And then pressure of all 3 compartments. And that goes for the cable compartment as well. So once we get into how our monitor is working, and I'm going to skip through a couple because I feel like my time is probably running very quickly to get in.
No, you've got another, Chris, you've got another 10 minutes.
Yeah. And I'm just now getting to the monitor, so I thought I should probably.
It's okay. Don't rush. Don't rush. Take your time.
Yeah.
We already have questions for you, so
okay,
keep going. All right.
Okay, so as I mentioned, when we were doing our routine maintenance, we used the old TCG method, and this is a picture of it just to show you. This was actually a McGraw Edison unit. There's some Tcg tubing that allows you to pull this bulb. You hand pump a gas sample out of that transformer. It's run through these bottles, and you can capture that sample here. And then it's run across a catalytic bead type sensor, and that would detect any type of combustible gas that was present in the headspace. So we're measuring gas. We're not measuring in oil, was the big point I want to make. And we used this for years. I was with the utility, like I said, in the field. I was actually doing this testing myself probably for 15 years of my career. And it was a fairly effective test. We would find problems quite frequently, and it saved us a few times on some that could have been a major problem. The only thing being with this is there's really no way to do this to the cable compartment due to the design of the transformer, and it not being pressurized. So, and that's where most of our failures were happening. We did find some main tank and switch issues using this test. And I just wanted to go that because I kind of wanted you to understand where I'm going with the monitoring, because I had gotten so used to that test and I had seen the effectiveness of it. And I thought, well, why don't we apply this to an online type process? That way we're getting down here, the transformer is being looked at 24 hours a day rather than once every 5 to 8 years when we can get around and get the whole system checked. So the vault safe monitor, actually it's a manifolded system that allows all these headspaces to be tied together. You can't mix the oils from these compartments, and that's in the IEEE. If you go and look at your IEEE, I believe it's C5712. These compartments, you can't have mixing of oil. So any type of oil monitoring was going to require that at least 3 sensors be purchased. So when you start talking about 3 separate hydrogen sensors and 3 separate pressure sensors, you're starting to get into quite a bit of money you're having to spend to get monitoring on transformer, to monitor the total system. So the thought was, we'll take the headspace and we can manifold these compartments together and run all this gas through a sensor chamber that's built within the monitor that lets us measure for hydrogen values. Also, this has now since all 3 compartments, the gas spaces are manifolded together, it allows us to do one pressure check too as well. So now we've kind of turned it into your substation situation where you have nitrogen fed systems. Again, these aren't nitrogen supplied, but they should have nitrogen placed on them and oxygen purged off when they're in service. But by putting the adapters, some adapters were made to fit into the gas sampling ports of these, and also one can go in the fill valve of the cable compartment. So I was able to effectively manifold everything together in the headspace, which now let me also pressurize that cable compartment, which was something we had not been able to do in the past. And that turned out to be a great thing. The first one I installed actually found a huge leak in the top of the cable compartment that the company did not know they had. And this was kind of their test plot. So they had pressure transducers on all these compartments. But yet, if you have a cable compartment that's not pressurized, well, zero pressure is not that, there's no difference between 0 in a sealed compartment and 0 in a compartment that's open to completely open atmosphere. It could have a huge hole in the top of it, and they both look the same when you're looking at pressure. So by pressurizing this compartment with the rest of the compartments with our system, now we're able to detect leaks, and that's done by, we set an alarm similar to what you would do with substation. You should have about a pound of pressure on the transformer during normal operation. And so we can set alarm points at a quarter pound, a half a pound. When you drop, the pressure drops down to the level, you can get an alarm into your SCADA, and then pretty aware that, hey, we have a leak occurring somewhere on this transformer. Go out and do your maintenance at that point. And so the hydrogen is measured from each compartment as well. As I mentioned, those cables breaking down, that's a big PD event, a lot of hydrogen generated. And one of the things I really recommend when doing this is I like to look at hydrogen as a rate of change alarm. And in these instances, well, in all instances, actually, because I've seen transformers where 100, 150 parts per million, pretty normal operating range for that transformer. What I'm concerned with is, did I gain 50 parts per million of hydrogen or 25 parts per million of hydrogen in the last 24 hours? I mean, when I see that type of event and that fast an increase in hydrogen, that's pretty much letting me know that I have some active PD occurring within that's or some type of sparking event that's starting to go on. And again, with these transformers being a secondary loop, there's no harm in getting them out of service. It doesn't affect your end customer. So when you get these alarms and you see that parts per million change, go on and take it out. Let's get it tested and let's find the problem. Because I think alarm response is a huge thing. I mean, alarms that are ignored are really, why did you bother with the monitoring then? Because you do see from this side of the industry, and even when I was at the utility, there's a lot of difficulty in getting these online, but they really can save you in these kind of cases, especially with a transformer with like this, where it's really not that big a deal to get it out of service. So I'm taking head samples of headspace. So these are gas samples, not oil samples that I'm taking. And so hydrogen, there's a little different, it works a little differently when you look at it in gas as compared to when it's dissolved in oil. So your DGA readings. So typically hydrogen it runs at about a 20-to-1 ratio. Of course, it is somewhat temperature and pressure dependent as to what that ratio to be, but 20-to-1 is a pretty typical number that you would see it at. So if you're measuring 50 parts per million in your oil, I would expect to see about 1,000 parts per million in your headspace. So you have a much greater concentration in the headspace as opposed to what you would see in oil. Also, it disperses much quickly in the gas. So when you're looking at hydrogen in oil, and if you've done much DGA sampling, you'll see a lot of samples where you may have methane, or ethylene is a great example because it's a very sticky gas. It stays in the oil for a long time, so its solubility rate's much higher. Whereas hydrogen solubility rate runs about 5% for hydrogen. That being said, it's also not homogeneously distributed instantly across that oil blanket. There's some things that have to happen with that hydrogen when it's produced in oil for you to detect it if you're putting a monitor at the drain valve of a main tank. So let's just assume that the fault that's occurring is on the opposite side of the transformer. So now we're depending on that hydrogen to be generated, and then whatever convection, and with these type of transformers, it's only going to be a natural convection due to heating of the coils and then passing through the radiators. It takes a lot of time for that hydrogen to disperse through that oil back to where that drain valve monitoring is located. And then you also have to remember this hydrogen, it's steadily trying to escape into this gas state. So it's crossing that gas oil partition, and you're getting a very high concentration of it in the headspace of that transformer. Again, about 20 times more than what you would see dissolved in oil if equilibrium is reached in that transformer. However, another problem you'll run into with this is you may have leaks on that transformer. So if you have leaks, now you have hydrogen escaping the atmosphere, which is where its natural state is. So that even prolongs that time to pick up the monitor even further out, because you're not getting that equilibrium due to the escape to atmosphere that you're seeing of hydrogen. And if leaks bad enough, you may not ever see it, because again, especially if it's a PD event where you're generating quickly, if it's generated in a gaseous state, that's going to go straight to the compartment, and then you do have to wait for that saturation back into the oil. So that was kind of the thought process around putting the monitoring together. Also, one of the advantages of this manifolding system was, with these smaller compartments, the cable and the switch, which we talked about, they're greatly affected by ambient changes in temperature. So if it gets really hot, I've seen switch compartments get up to 7-8 psi of pressure in that compartment if the compartment's sealed well. And again, the cable compartment really doesn't give you any type of pressure measurement, so you really don't know what you're looking at there. But I can guarantee you that as it gets hotter, very small compartment, very small gas space, you're seeing a lot of pressure being generated as that oil and gas expands. And then during the winter, you would go down, and it was not uncommon to see things being in some state of vacuum, due to the colder ambient temperatures. So -2, -3 psi. Now, this creates another problem with the transformer, in that you're steadily pushing and pulling on these gaskets. You're applying pressure, and then you're sucking in on them, and then you're applying pressure, sucking. So you get wear and tear of that gasketing system, and it just expedites that chances of moisture ingress and having leaks. However, with the monitoring we built, since now everything's manifolded together, we now have that much larger compartment of the main tank where your core and coils are contained. So it kind of equalizes out across, the pressure is able to equalize out across all the compartments, and you don't see such a rapid swing from vacuum to overpressure happening. And we do provide a output that lets you know what that pressure's at. Again, alarms are set for low values of pressure, because we do want to catch a leak, and that could be an oil or a gas leak is going to result in that low pressure. But we also want to know, we don't want something out there with 10 psi on it either. I mean, that's also problematic. So that allows us to watch that across all three compartments with the monitor. And we've talked about this, and this was the old Tcg tester. And again, this was kind of the birth of this idea, came from running this test. I've talked about, I've outrun myself on my slides, and I always do that, and I apologize. But so communications we'll talk about briefly, since I have not, and it is on this. Generally, I like to set these up, and they're configured. Again, I like to set hydrogen on a rate of change alarm. Pressures, I generally like to set about 1/4 pound for low pressure alarms. And those are alarms that can be inputted into the monitor. There is a command line that you can enter. You do have to do that locally when the monitor is installed, but you can set these values. You can also set it for a total PPM value. So if you want to go by IEEE guidelines and say, going from condition 1, condition 2, I would like alarm, and set that at 100 parts per million, you can do that. I would recommend at least getting some type of history for a transformer before setting a total PPM alarm, to eliminate false alarms, because again, 100, 150 is not that unusual for some transformers to see. So communications out of this unit, we can go out via Ethernet or serial. There are some analog outputs as well. And then for protocols, it's available in DMP and Modbus. So combustible gas, we've talked a lot about hydrogens. You do get your alarm. So what do I do then? Well, again, the first thing to do is let's get this transformer out of service, and let's find out where our problem is. So we're getting our alarm in the gas space. So how do I know? So hydrogen monitoring start with, that's a smoke detector. And that's any hydrogen monitoring on any transformer. There's not a lot of analytical value to be gained from looking at hydrogen alarms. That just kind of tells you something's going on, kind of like your smoke detector tells you something's on fire in your house. It doesn't say which room it's in. So when we get these alarms, we need to get these transformers out of service. Let's go out, let's pull some DGAs, let's do some offline testing to determine where our problem's happening. So just quickly running through, with hydrogen, I would expect to see some methane development. They both start generating around 150 degrees C. So I would expect to see that. Where we're really looking is also if we have acetylene. So if we have acetylene building up and we have ethylene, and ethylene about 10% of our acetylene values, we have some active arcing occurring with that transformer. With hydrogen and mostly methane, we know we have probably a PD type thing occurring. So by pulling these DGAs, once we had this out of service, we've had our warning, we get our transformer out of service, we pull our DGAs, and we can pretty much determine, well, there's a lot of gas saturated in oil in, let's say it's the switch compartment for this transformer, because again, with the way gases are, the solubility rates, where it's being generated, it's where the DGA is really going to show those high values of that gas. So that would be what I would recommend. And again, if you want to go through another for another time, doing analytics concerning, you know, what the ratios of gases are as to what type of problem you would have. Also looking at carbon monoxide and carbon dioxide, determining some of your cellulose involvement using those. That would be a topic for a whole nother discussion, and we don't really have time to get into that too much today. But that would be the primary thing I would suggest we go through to determine. So lastly, just to go through what's hydrogen, and we talk about hydrogen works a little differently when we're looking at gaseous state versus and in oil. So one of the things is how quickly it disperses and the higher concentrations that we see in gas. So we have a much quicker dispersion rate occurring. We have a much higher concentration of the gas present, which that leads to earlier detection and more reliable sampling or more reliable detection, because we're not counting on that convection of oil to get that hydrogen gas around to wherever our sensor location is mounted. When it hits a gas base, it's a pretty even dispersion across that gas blanket. Also, there's the sensors themselves. So it takes the sensors in oil, and this was actually some that were placed in oil, and you can see there were 15 sensors placed. 5% hydrogen mixed in a nitrogen base was sparged through these sample cells, and you can see that for measuring in gas, where we're taking our gas measurements, we're about 1 hour till we reach that full saturation point at the sensor. So 1 hour's worth of time. Whereas if we go to 15 sensors that are installed in oil in the transformer, we can see that that's up to about 50 hours before we reach that full saturation. Now, this is also being done in a very predictable lab setting where we're not dealing with leaks or that type of things. So again, if you get out in the real world, almost everything leaks at some point. That's going to cause this to be even slower, as we're not going to get that equilibrium. So this is the vault safe installation. As you see, it goes on top of the transformer. It can be mag mounted. So that even puts it further out of the flooding. However, it is submersible as well. And the hydrogen and pressure sensor are contained within the unit. We can see that we are manifolded in the front, where we can run out, and we've got samples going over to our main tank here. We're grabbing our cable compartment right here, and we're grabbing our switch compartment right here. These silica bronze pressure adapters were something this utility already had in place, and are not part of the system. Again, we only use the one pressure transducer, and it's actually located within the box. We use a polycarbonate box it's just more effective against corrosion. especially when we start looking at oxidizing agents, salt solution. The adapters are all silica bronze that go, and these adapters go into existing ports in the transformer. So again, you're really not making any modification. I've done several of these by myself, and there's actually a video on our website if you want to go to it. It takes me about 45 minutes to put one in. So I'm going to just kind of run to the end of this. Also, we can do some a mag mount RTD. That's optional. If you would like to bring temperature in, we have some inputs available to do that as well. So you could look at top oil temperature to see how that flux of hydrogen between oil and how it's being affected by temperature. If you wanted to bring that in, that's also a good thing to have to look at. If you want some more information, please reach out and contact me by all means, but you can also go to our webpage, and these are instructions on how to get things. I've got a white paper there. There's a video demonstrating how this works. So some very useful information there. Okay, any questions?
Okay, Chris, great. Thanks for the presentation. First question, how often did you perform DGA on network transformers? Was there any safety concerns about taking a sample from an energized transformer?
It depends on when you came in my career. It's if there were safety concerns. So when I first started, we did a lot of things that probably shouldn't have been done. At the end of my career, when I moved more into the asset management, again, we were running this TCG test. So that was the main test we were running. We would take some oil samples for dielectric. Again, there's always a risk, and it's no different than a substation transformer. I mean, transformers can fail. But no, I mean, as long as you have positive pressure, what you don't want to do is you don't want to open anything up and have a vacuum. That would be the hugest risk that's involved. We did a lot of sampling of line regulators as well, and that would be another huge issue with those. And I completely got away from that at the end of the career because I felt like it just posed too much risk. But with these, if you are going to take a DGA sample, you need to be for sure that you have positive pressure on that transformer before we're pulling that sample. If not, if you're in a vacuum, if you go in the wintertime, that transformer is in a vacuum, you're going to immediately start sucking air up through that transformer, which can find its way in between live parts and will result in failure. So that would be the main safety risk I would say associated with that.
Okay, next question. Hydrogen generation is a common aging process, and one reason why some do not rely on this type of monitoring due to nuisance alarms. How did you address this?
And again, the way I've done that is I like to look at it as a rate of change. I know exactly what you're saying with these nuisance alarms with that, because you do generate hydrogen. However, like I said, you shouldn't see a 25 parts per million production of hydrogen over a 24-hour period. So I like a daily rate of change alarm when I'm looking at these. Again, I will set up a ppm alarm depending on the transformer and how it's been running. But what I'm really concerned with is what's happening today. If I see something abnormal, so, when you talk about normal aging process, you're generating, a couple parts here, a couple parts there. You might go from 20 at the first year, you might be up to 28 at the end of the year. And then the next year, you might be up in 35. So it's a slow process when it's due to natural aging. When you have an event occur that needs attention, I feel like you generate quite a bit of this over a 24-hour period. And that would be how I would deal with these nuisance alarms.
Okay, thank you very much. Good presentation. Thank you for the questions.